All right, let's talk 10.1, difference in proportions. Difference in proportions. And so we're going to be doing two things here. We're going to be doing both our confidence interval and our test of significance. Okay, so this is chapter 10.1. Here's the general idea, folks. We have population number 1 and population number 2. Right? I'm trying to figure out, is there a difference between these populations? And we're going to be specifically looking for proportions from this one and from this one. And when I'm talking about the difference, I'm trying to see, is there actually a difference, right? First and foremost, we need to make sure that they are independent populations. Right? That means they don't completely interact with each other, right? So we want to talk about things like, say, Lake Ridge High School and West Linn High School, right? I want to say, well, the proportion of students who take AP exams at Lake Ridge High School versus the proportion that take place at West Linn High School. Because you see, if we were to take the difference in the proportions and that difference equals 0, that means there's no difference. But if the difference was something other than 0, that means either Lake Ridge has more or West Linn has more AP students, right? So proportionally, that's what we're going to be looking for. That's the general idea, okay? So what I'd like you to do, take your formula sheet. If you go find your formula sheet, or I have it right here on this guided notes if you'd like that too. A couple things that we can take and look at, okay? One of the things that we want to use to help assess this is the formula sheet, right? Because here's one of the deals. If I'm trying to do, say, the Z statistic on the formula sheet, and I'm doing it for a one population parameter for proportion, I'm going to kind of go down this row right here, right? So if I needed to find a Z score, I'm going to go Z equals P hat minus the null hypothesis over, and there it's giving me the formula for what I need, right, on the bottom, right? Now, again, if I have to use the sample in place of the population, there it is there, right? So they're kind of showing you, is it this one or is it this one? All right, it depends on that. This is actually called standard error and no longer standard deviation if you're using the sample stuff there, right? So that's something to kind of take note of. Now, here's the other thing that we're going to be looking at. I'm going to look at for two populations. That's what we're doing now. And if we're going to end up subtracting two populations, then I am going to look at these things here. And, oh, the standard deviation. And, oh, the standard error. Right? So these are the different things. Look at all these different things that we have here. So these are things that we're going to want to take note of right now. So that the reason that we do these notes right ahead of time is just so that we can jot down some notes. So when we hit the class running, we have something to work off of, right? So here we go with this one here. All right, I'm going to be using these formulas here in just a minute, okay? Formula sheet. If you look down kind of at this other piece that I have cut off here, this is for samples. Sample means, right? So we're not using this stuff right now. So let's just ignore for now. Now we're going to use that on the next class, but not on this class. So let's ignore that and let's just focus on this piece. And we're also no longer talking about one population. Now we're going to be looking at two populations. So let's ignore all that stuff. So we're going to just be kind of like in this realm here and here, all right? So let's talk about how we're going to use those. So first and foremost, what are we talking about? The difference in proportions from two separate populations, independent populations, actually. I'm going to pull p hat 1, I'm going to pull a small sample and find a proportion there. I'm going to pull a p hat 2 over here. Okay, so that's kind of the idea. All right, we're going to use this note sheet to help us out, this formula sheet to help us out, and let's talk about it. All right, so let's talk confidence interval. So what do we need to know about creating confidence intervals for proportions? Well, panic. That's always a confidence interval link. Panic, right? And remember, we talked very specifically about the A, the I, and the C have to be spelled out specifically when we're doing one of these problems, okay? So let's talk about the A. Those are the assumption checks, right? So if these are the assumption checks, here's what we know about proportions. Only we have two population proportions, so we actually have to double up our assumption checks. So check this out. We're going to do something like this. We're going to go population 1, and then we're also going to take a sample from population 2. So in population 1, what's the first thing we need to do? We need to make sure that n times p is greater than or equal to 10. And we're talking about the sample from the first population and the p hat from the first population. N1 times 1 minus p hat 1 from the first population, make sure it's greater than or equal to 10. Well, if I'm in the second population, I'm going to take the sample from the second population, the p hat from the second population, make sure that's greater than or equal to 10. And we're going to need to do the same thing, 1 minus p hat greater than or equal to 10, okay? Number 2, you're going to make sure you got a, random sample from population 1. And over here, wow, I am really just a little bit off. Hold on, 2. That should be a 1 up here, okay? Make sure this is random, but from the second population. And number 3, we will end up doing the 10% rule from the first population, and we'll do the 10% rule from the second population. Okay, so it's literally doing what you were doing back in chapter 8, only double up. We got population 1, we got to make sure that that's kosher, we got to make sure that that's kosher. So they both have to actually match, right? The requirements need to match, so then we can subtract them and we'd be okay with them. Okay, so now let's talk about the interval calculation. So let's write this down. Let's write down the formula for interval calculation. So this is kind of where I use the formula sheet to help out, okay? So what is it that I'm actually after? Two populations, and I'm using their sample differences. Everything is about the differences. So P1 minus P2, only we're going to have hats to use on this. So let's write this. Let's go P hat 1 minus P hat 2, okay? So this right here is called the differences. Okay, difference in proportions. And then it's going to be plus or minus. Remember that proportions are always z, So I'm going to go look up a z star, right? And we'll go do that on our t table. Remember, that's the thing that we use on that. But times, now we need the standard deviation or standard error for this certain thing. So that's, I'm going to go back to my formula sheet. Okay, so it's essentially this thing right here. Or sometimes we just look at it like this, right? Because we're going to have to use the p hats in the place. Now it says use this as the standard deviation, or when P1 is equal to P2 is assumed. Well, I'm going to tell you right now, for a confidence interval, we're always going to use this. Unless there was some weird thing where they said, oh, hey, guess what, guys? P1 is equal to P2, right? Yeah, I don't know why it would say that. So it usually doesn't, not for confidence intervals. Confidence intervals, boom, we just want to use this formula right here. So we're literally going to put that formula together. So that is what our standard deviation, boy, that looks complex, doesn't it? So we're going to go the square root of, you ready? P hat 1, 1 minus P hat 1 over N1 plus P hat 2, 1 minus P hat 2 over N2, right? So there it is, right? So there is your formula for the confidence interval for the difference in proportions. And then conclusion, Guys, I think we know this one, right? It's we are blank percent confident the interval from blank to blank captures the true difference in proportions context. All right, just finish it off with some context there. Okay, so that's it. So notice this merging of ideas that we did from chapter 8, confidence intervals, and then we also did this when we did some combining of distributions. And when did we do that? Back in chapter 6, right? So a while back when we started thinking about, oh, how do I find the standard deviation when I combine two distributions, right? So when I'm looking or comparing for two. So this is kind of the real important piece right here, right? Kind of sketch these things out, and then we'll do it right here. All right, you guys ready? Here we go. 1990, 551 of 1,500 randomly selected adults indicated they smoked. In 210, 652 of 2,000 randomly sampled adults indicated they smoked. Use this information to construct and interpret a 95% confidence interval for the difference in the proportion of adults who smoke in 1990 and 2010. So we got two separate populations here, right? 1990 and 2010, right? These populations. So I'm going to call, all right, I'm going to keep this color coded for you. P hat 90. Can I call it P hat 90? P hat 90 is equal to 551 over 1,500. So if I put that in my calculator, 551 divided by 1,500. So get that going there. That's 0.37-ish, right? I'm rounding that. And let's call P hat, I'm going to call it 10, P hat 10 for 2010 equals 652 of 2,000. Now notice the sample sizes are different. No big problem, right? Let them be different. That's not what we're after. We're after just trying to look at those numbers. 0.326. Okay, so let's kind of start there. All right, now here's another key word that we like to look for: proportion and difference in the proportion, right? Difference meaning that we now got to combine the two by subtracting. So we're going to get right into our assumptions because we are doing a 95% confidence interval, so I'm thinking panic. And what are the three parts that you need to explicitly show? The A, the I, the C. Okay, so if you want to, I like doing this like little T table here. And I'm going to call this 1990 over here. I'm going to call this 2010 over here. All right, so then for 1990, here we go. We got to do the check, make sure it's going to come out normal. So I'm going to go 1,500 times 0.37, make sure it's greater than or equal to 10. I'm going to go 1,500 times 0.63, make sure it's greater than or equal to 10. Yep, those are big numbers, right? I'm going to go 2,000 times 0.326, greater than or equal to 10. I'm going to go 2,000 times 0.674, greater than or equal to 10. Yep, those are big numbers. Number two, let's see, random sample. Right, random sample, yep. Let's see what they say. In 2010, randomly sampled. Yep. Okay, so now we know there should be unbiased as we combine them. And then number three, 10% randomly sampled adults. Adults. So we're going to say all adults in 1990. What is going on here? 1990, my pen wasn't working, sorry, is greater than or equal to 15,000. Multiply 1,500 by 10. I think that's safe to assume in 1990 there was that many adults. All adults in 2000 greater than or equal to 20,000. I think that's safe to assume as well. All right, good. There we go. There's our assumption checks. Grand. Let's go to the interval calculation, okay? Now we're going to use this basic idea right here, P1 minus P2, and then we're going to start looking up all the things, right? So let's do this. P1, I'm going to just call 90 my P1, and my P2 is going to be the 2010, okay? So I'm going to go 0.37 minus 0.326, right? Plus, minus, Z star. Go look at your Z or the T table, go down to the infinity line and find 1.960 above the 95% critical value level. And now this, I'm just going to type this, or I'm going to write this in, but I'm going to let my calculator actually do the calculations for me. But just for AP sake, let's do it. 0.37.63 over 1500 plus, that's P90, 1 minus P90 over N, right? And then I'm going to come and take the other one, 0.326 times 0.674, right? And I am going to put that over 2,000. All right, now I got it set up. Now I just need to calculate that thing out. And you could do this by hand, but instead of doing it by hand, ain't nobody want to do that. Let's use our calculator. So in your calculator, here's where I'm going to go. I'm going to go stat. I'm going to go test. I'm going to go stat, test. I'm going to go all the way down. I'm going to find it real quick. 2, because we're doing 2 populations. Prop, because I'm doing proportions. Z, int. 2 prop. 2 samples from 2 populations, proportion, Z, because it's always normal, always Z, interval. Go ahead and do that. So what's it call for? It needs a couple different things. It needs X1, it needs N1, it needs X2, it needs N2, it needs C level, right? So it needs all those things. Okay, so let me see, X1. Here we go. So that I called P90, right? 1990 was my first one, so 551, and the sample size of that was 1500. And then 2010, 652, and there was 2000. Okay, let's try 551, 1500, 652, and 2000. And then my confidence level is 0.95, my C level, so 0.95. And then let it produce a value for you. Here's what I get when I do mine in my calculator. 0.00944 all the way up to 0.07323. I had to make sure that I had punched everything in right, okay? Now, here's what I want you to think real quick. This is representing the interval for the difference in the proportions, okay? So remember, if you were to subtract the 2 and then create an interval, this is the interval that we believe the true difference is. Now, notice that they're both positive numbers, which means our interval believes that if we're going to get a positive number, that means the first number was always bigger than the second number, just mathematically, right? And so if my interval is only positive numbers, then I believe that the first is always going to be a bigger number than the second because I never got into the negative values. All right, so think about that if that challenges you a little bit. Think about what I'm saying. If the bigger proportion, the first proportion, is always bigger than the second proportion, right, to kind of keep that going like that. All right, now let's conclude this. We are 95% confident the interval 0.009 to 0.07 captures the true proportion, true difference in proportions between the smokers in 1990 and 2010. All right, so there it is. So here's the key, the big critical piece though. I want you to always look at your interval and see, does it capture the value 0? Is 0 in here, right? That's the biggest question, because if 0 is in there, that means it is possible that there is no difference between the 2 years. If 0 is not in here, that means we actually believe there is a difference between the 2 years, and then we can assess which one has a bigger proportion or whatnot. So this is the kind of the question I want you to always kind of ask: is 0 in this difference in proportion confidence interval? Okay, let's move on. Let's do the next one, phantoms. Let's talk about which ones are different than our normals. All right. So again, when we are doing phantoms, we are usually really only talking about the hatums. Okay, so the hatums. So let's talk about, for proportions, what is our null hypothesis? Now, this is what's great about difference in proportions. Even though they're bigger and whatnot, they're standard. So what we have, the standard is that the proportion from population 1 is equal to the proportion from population 2. Or sometimes people like to write it like this: proportion 1 minus proportion 2 is equal to 0. Yeah, now you can see, you can write it either way. They're the exact same. So then proportion 1 is either going to be greater than, less than, or not equal to proportion 2. Or we could do the same thing. P1 minus P2 is either greater than, less than, or not equal to 0. That's it. So this is always going to be standard. So when you're doing a difference in proportions to independent populations, then you don't have to really think too hard about what it is. You're just going to remember that P1 is equal to P2 is what we're standardizing, and we're saying, okay, let's test that. So then you got the assumptions that we just talked about above, so it's going to be the exact same. Let me just scroll up real quick. And we're going to do something like this, almost the identical thing right here, right, for our assumption checks there. All right, so then the TO part of this, right? So this is the actual calculating of the statistics. So what does the TO mean? It means that we are always going to build a curve. We're going to put the 0 on here. Why? Because of this right here. The assumption is always going to be that if I were to subtract the two proportions, it equals 0. And then what we'll need to do is figure out, do we put the number over here or over here? And then do we shade away? Do we shade away? Right, those kind of things, right? So we have to figure that out. So what is the number that we're actually going to put on one of these? It's going to be wherever p hat 1 minus p hat 2 exists. Right? Where is the sample difference? Because we put the sample on top of the claimed difference. And then the z-score that we're going to do, because it's always z, because it's proportions, is, all right, you ready for this? P hat 1 minus p hat 2 minus the claim. What is the claim difference? 0 every single time over standard deviation. All right, now if I'm looking for standard deviation, what am I going to do? I'm going to come back to this right here. Okay, standard deviation. So I always like to look at this one right here. But check this out. When P1 is equal to P2, when P1 is equal to P2, then we have to use these ones. Wait a second. Let me go back to this. Did you just say when P1 is equal to P2? Look at our claim. Oh boy, our claim is P1 is equal to P2. So if our claim is P1 is equal to P2, then we're going to use this. That it's going to say the combined P hat value times 1 minus the combined P hat value times this junk over here. And what is the P hat combined value? Well, that's simply putting the two together, right? So look at this individually. This right here is my P hat 1. This right here is my P hat 2. And what they're saying is actually just combine them as if they were from the same population, because the assumption is they are the same population, right? So that's just a nice idea to think about in there when we're doing this. So what does the bottom of that formula look like? It is the square root of the P hat combined times the 1 minus P hat combined times 1 over N1 plus 1 over N2. I guess there's a parenthesis there on that. Okay, so there you go. There it is. How do you make a decision? Same way you made a decision. Compare to your alpha value. Summarize. It's going to sound kind of like the this, because we're going to be talking about the true difference in proportions, but it's going to be with context based on your decision that you're making. Okay, so let's do it, you say? Let's do it. School official suspects the difference in the proportions of students. There it is. Difference in proportions of students who own technology devices between Lakeview North and Lakeview South High School may be a result of a difference in the social economic status of the students in the two schools. The result of a random sampling of the students' records indicate blah, 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 right? So there's a lot of stuff. Do the data, here's the actual question down here. Do these data provide convincing evidence that the proportion of low-income students at Lakeville North is higher, greater than, the proportion of Lakeville South? Use a 5% significance level. Okay, you guys ready? Let's do it. Hadams. So H, what's my null hypothesis? Well, we actually have two different things here, right? We have Lakeview North and we have Lakeview South, right? So those are actually the two that we're talking about. So watch this. Instead of doing ones and twos, why don't we just do something like this? The true proportion of North is equal to, because it's always equal to, the true proportion of South. How about I use N and S? Okay, just to help me out a little bit when I'm doing this. Okay, so then proportion of North. So I'm going again. That the proportion of low-income students at Lakeville North is higher than the proportion of Lakeview South. So they think it's higher than the proportion at South. Okay, that's it. There's our hypothesis. All right, assumptions. This is exactly how I do my assumptions again, right? I like to do the little table form of assumptions to get us rocking and rolling, just so I'm keeping them separate. So again, I'm going to kind of come over here. I'm going to say North versus South, and I'm going to just chalk these things up, all right, real quick. All right, let's go. Here we go. So North, what do we have? We have, I'm going to have to calculate this out real quick. So P hat from the Norths are the result of the random sample of student registration indicated of Lakeview North. So 28 over 120. So if I do that, 28 divided by 120, I get 0.23. And then what do I have here? P hat South is 30 out of 150. So that's exactly 20%, 30 out of 150, so that's 0.20. Okay, all right, North, here we go. N, it's 120 times 0.23. Now, if I had a P value to use, now notice they don't give me a claim for P and they don't give me a claim for P. We're claiming that they're equal to each other. So I have to use P hat in this place because I don't have the other thing to use, right? So if you have P, use P. If you don't, use P hat, right? That's always our standard. Okay, so that looks good. What about at South? South, it looks like it's going to shake out nicely as well. Okay. Good, good, good. All right, number 2. Did they take random samples on both? Random sampling, yes. Random sample, both of these. Yeah, okay. So if they do that, right? So random sampling of student registration that came from the house. So I can actually just write this. Watch this. What if we just said random sample, right? All the way through on those ones, right? That helps. And then let's go here, number 3, 10% rule. So all students at North, and that's just my abbreviation for Lakeview North, greater than or equal to 1200. That's safe to assume. Over here on the third one, we're going to do all students at South greater than or equal to 1500. That's probably safe to assume as well. Okay. All right. There we go. So now, if I wanted to name this, what's in my calculator, I might just say what I'm going to be using my calculator. Check this out. I'm going to stat test. I'm going to look down until I find the 2 prop z test. 2 prop z test. All right. Now let's do the actual test statistic. So here we go. I'm going to do something like this. I'm always going to put it over 0 for these things because check out the null hypothesis. It's always that there is no difference, that they are the same. So let's put it there. I'm going to worry about the shading and stuff in just a minute. So I'm going to start my z-score. Z is equal to, I know it's p hat north minus p hat south. Right, so that's kind of the first part minus 0. So I actually don't even have to put the minus 0 if I don't want. Okay, and then I know that I'm supposed to use, remember, this function, because P1 is equal to P2, use this one right here. But watch, my calculator will give me some values to plug in here. So at this point right now, since it's getting a little bit lacking over here, I am going to let my calculator do a little bit of work to catch me up here. All right, let's do this. 2 prop z test. Go for it. 2 prop z test. All right, I'm going to type in these x1, 28, n1, 120, x2, 30, n2, 150. What did we say that our sign was supposed to be? Oh, it's supposed to be greater than. So make sure you have greater than sign. Hit the calculate. Okay. So here's something I'm going to do right away is I am going to look at this. So here's the different values my calculator gives. It says z equals 0.6626. It says p equals 0.2537. It says p hat 1 equals 0.23, which we knew that already. P hat 2 equals 0.20. We knew that already. It says p hat. This is our p hat combined value that it's going to give us now, 0.2148. And then it goes on, it says N1 and N2, which we already knew those as well. So again, let me highlight, this p hat value is actually the p hat combined value that I want to use in that form right there. So I'm going to say this, I'm going to go based on the formula and this combine, I'm going to say 0.2148 1 minus 0.2148, as if I'm going to calculate that out, times 1 over N1 was 120 plus N2 was 150, and I'm going to close that out. Now check that out. It looks like I'm doing something, equals z value, there it is, 0.66. Done, right? Check that out. All right, let's now get the p-value. The p-value is literally listed under the z-value every time. 0.2537 is what that is, okay? And now, let's go back to the curve. I haven't drawn anything on the curve. Go back, if you will, with me, with your calculator, hit Stat, go over to Test, go down to 2 prop z test, the same place we were. Everything's still punched in for you. Now, instead of going to calculate, look at the very bottom. It says calculate, slide over to draw, and let it draw the curve for you. Look how it tells you, so it's going to go, because my Z-value is 0.66, you're going to go roughly 0.66 standard deviations. How far is that? Who knows? It's about right there, right? You're going to go roughly that 0.66 standard deviations, and you're going to shade to the right. Copy what's in your calculator, because the shading is the proof of what's going on. There's your T and your O all together, your phantoms. All right, let's make a decision. M, since 0.2537 is greater than 0.05, remember that was the alpha level that they're asking us to use. Since it's greater than that, what do? This is the same thing we were doing last chapter. Fail to reject the null hypothesis. And then summary, it always sounds like this. We do not have enough evidence to suggest that low-income families at North is higher proportion than South. There we go. We do not have, because we failed to reject, we were not able to say that. Nope. We had to stick with our, ultimately, we kind of have to stick with that. We do not have enough evidence to suggest, because that's what we were trying to. We assumed that. That's it. That's your 10.1 right there. All right? In class, we'll do some more examples and ask questions.